A warm welcome to everyone who has now joined this Euclid pre-launch press briefing we're having here today online. Euclid will explore the dark universe and is targeted to launch on a SpaceX Falcon 9 rocket from Cape Canaveral in Florida, United States at 11:11 local time or 17:11 Central European Summer Time on Saturday, the 1st of July. We're currently foreseeing a backup launch at the day after. I have with me today a few guests and a few speakers that can talk about the fascinating world of Euclid, as I would call it. With me today are Giuseppe Racca, who is the Euclid project manager from ESA. Also from ESA is René Laurijs, who is the Euclid project scientist. We have Yannick Millier, astronomer at the Institut d'Astrophysique de Paris and the Euclid Consortium lead. Guadeloupe Cañas, who is a research fellow at ESA, and Paolo Musi, who is the Euclid program manager from the Prime Thales Alenia Space. A warm welcome to the journalists that have joined, and a warm welcome also to Giuseppe Racca, who will start giving us a short introduction to the mission. Welcome, Giuseppe.
Good morning, good afternoon, everyone, depending on where you are. So starting with explaining a cosmology mission like Euclid is, I cannot avoid starting from this embarrassing situation that the cosmology lingers today by observing that only 5% of all the universe is made of is actually atoms and particles that we are all made of. All the rest, the 95% is made of other things which we don't really know, dark energy and dark matter, typically as they are called. We also know already a little bit more about the universe. We know that about 13.7 billion years ago it had origin, and it has expanded since then. So it never stopped this expansion. First, the expansion was very, very rapid in the time of inflation. Then it was slowing down. And then from recent observation, it has been seen that actually the expansion has started accelerating. And to explain this latest acceleration, the cosmologists have basically introduced the concept of dark energy, an energy that should produce this force, this repulsive force, to allow the universe to accelerate. In these last 10 billion years. And in fact, this is really what Euclid wants to observe, is to observe last 10 billion years from when most of the stars and the galaxies are formed, and going across also the period in where the dark energy started to be predominant. If you want to do a cosmology, let's say, if you want to start, let's say you want to observe the cosmos as a whole, then of course you need to take a big survey. It's not enough just to make some very detailed and accurate observation of a part of the universe, but you really need to make a big part of it. And Euclid is especially designed to really cover with a very wide angle telescope to cover most of the universe that can be observed in a very short time. The field of view of Euclid is 2.5 the size of the moon, and it can cover the extragalactic sky in about 6 years. This is about 36% of the entire sky around us. All the rest is actually occupied by the stars of our Milky Way and by the dust in our solar system. Euclid is really specially designed, as I said, to do that very quickly in 6 years, to do all this amount of survey that, for example, for other telescope like Hubble Space Telescope, it would take about 1,000 years to do the same job. And while when you use a wide field camera, you typically have distortion at the edges of the camera, Euclid is really particularly designed and constructed to be very precise, very sharp, and no deformation in all part of the field. Everything is always in focus. But not only we want to observe the universe in wide, but we also want to go deep. Let's say we want to go deep, as I said before, about 10 billion years. And this going back in time, it corresponds to going far away. And since the light takes a finite speed, and therefore it takes some time from when it was originated to arrive to us. Going back in 10 billion years, it means going approximately 10 billion light years away from us at the moment. Since the universe is expanding, also the wavelength of the light that comes to us gets stretched. And therefore, in order to observe far away, we also need to have a near-infrared instruments. Therefore, we have a complement of two instruments, one invisible, VIS, and one in the near-infrared, that with the combination of these two instruments, we can have actually a map of a 3D map of the universe and a 3D map of the distribution of all the visible matter, let's say all the galaxies. Instead, the dark energy and dark matter will be derived from this observation, but in a indirect way, and this will be explained later by my colleagues. This is just a view of Euclid. Euclid is about 2 tons spacecraft. It's made of 3 main parts. Let's say the payload module, which contains the telescope and the instruments, the service module, and the sun shield. It's about 4.7 meters tall and 3.7 meters in diameter. We will position Euclid into the Sun-Earth Lagrangian point 2, which is 1.5 million kilometers away from Earth in the direction opposite to the Sun. It will be launched by a Falcon 9 from SpaceX on the 1st of July, and it will take about 1 month to reach this halo orbit around L2. When we speak about a large program, particularly complex like Euclid, we really speak about cooperation among many partners. And as you can see here, in red is the overall responsibility of ESA, but the green part is the responsibility of the Euclid Consortium, which has provided the 2 instruments. And one thing I would like to particularly highlight in this case is that in the ground segment, in addition to the space segment, which is the spacecraft and the instruments, the ground segment is particularly important for Euclid. And not only the operational ground segment, which is under the responsibility of ESOC and the Science Operation Center under the responsibility of ESAC, but the science data centers. We have 9 of them, 8 in Europe and 1 in the United States, and they are incredibly important because it's only through the post-processing of data that the indirect measurements of dark energy and dark matter can be performed. And this will also be explained by my colleagues later on. Finally, just a couple of numbers. In Euclid, 300 science institutions have been involved in 21 countries. 80 industrial companies have been involved through 140 industrial contracts, and we estimate that around 3,500 people are currently involved in that. And the total cost of the mission overall is in the order of 1.4 billion euros. Now we go with the next presenter, René Laura is the project scientist, to detail a little bit more why Euclid is in reality really so special.
Yeah, thank you, Giuseppe. Yeah, some time ago, and it was in 2007, ESA received 2 proposals basically, and in the end we got one big experiment out of it we call Euclid. Dark energy and dark matter reveal themselves by the very subtle changes they make to the appearance of objects in the visible universe. Otherwise, we don't know about them. They must show somewhere, and it's very subtle. Otherwise, it would have been discovered earlier. Euclid wants to measure the dark energy and dark matter with unprecedented high precision and accuracy. And how do we achieve this? So the mission is the combination of several optimized components. And we have weak lensing and galaxy clustering, and this will be explained in more detail by Yannick, the next speaker. These are 2 independent dark energy measurements methods to ensure that the scientists understand possible systematic errors in each method. Now, from a more hardware point of view, the design of the Euclid mission combines the best performances of the emission elements to end up with the most sensitive dark energy detector, I would say. So it's more than a space telescope, Euclid. It's really a dark energy detector. So now I'm having some illustrations. Slides. Share. Sorry. Okay, we have seen the L2 orbit, but very important for Euclid is that the L2 orbit provides the best observing environment. And high accuracy measurements require that all mechanical components must be extremely stable during the mission. And L2 can provide this. L2 also enables us to see the whole sky. And since Euclid is a sky surveyor, it's an ideal place for a mission like Euclid to have more than one third of the sky viewed with extremely stable conditions. Now, the payload consists of a telescope with two scientific instruments. The telescope itself, the mirrors as well as the structure, is made of silicon carbide, which is quite unique for this telescope, because silicon carbide has the properties of a ceramic, but also the properties of a metal. The ceramic properties give it very good stiffness of the telescope, and the metal properties gives it a good heat conductivity, so that possible changes in temperature, but also in mechanical stresses are really well taken care of by this material. Now, everything we can build out of silicon carbide has been built out of silicon carbide in the payload, and that is the instruments have silicon carbide, the structures, as well as the whole telescope itself, as well as the base plate on which the telescope and the instruments are mounted. The visual instrument, which you see on top, is a 600 megapixel camera, CCD camera, to give a large amount of information of the field of view we cover. And we also have a near-infrared instrument, which has 64 megapixels to cover the same region of the sky as covered by the VIS instrument, but then in the infrared. It can do both imaging and spectroscopy in the same time. The instruments are designed such that the camera fields cover a large area, as I mentioned before, a large area on the sky. And I give you a comparison between Hubble and Euclid. And as you can see, Euclid can in one go cover a field much larger than accessible by Hubble. Now, during its entire lifetime, and Giuseppe already mentioned it, Hubble did not cover more than 100 square degrees. And this can be done by Euclid in 10 days, basically. So in order to get our 15,000 square degrees, which is the size of our sky survey, we need making these big images of the sky. Otherwise, we cannot make it in 6 years. We also have reaction wheels, which we stop in order to minimize the vibrations of the satellite, so that we can make the sharpest images possible. And we use cold gas thrusters on the satellite, and maybe it will be mentioned by Paolo later, in order also to minimize the vibration, but still to compensate the tiny force of the radiation pressure by the sun. Also in order to make the sharpest images you can get. So everything has been built inside the satellite in order to give you the best imaging. In the previous slide, I show one field, which is the size of about 2 full moons. Now, the Euclid Sky Survey consists of 40,000 of these fields, and it will be covered in 6 years. To monitor the stability of the main survey of these 15,000 square degrees, we have also deep fields, which are about 50 square degrees of the sky, where we on a regular basis monitor the stability of the whole survey of a period of 6 years. Since we monitor it so often, it goes quite deep in the deep fields. That gives the astronomers also a unique database to peer very deeply into the universe for on 50 square degrees. The information contained in one field is about 5 gigabytes of raw science data, and this is compressed. So in total will be 10 gigabytes of information per field, which I showed. And for 40,000 fields, you can imagine how much data that will be. Per day, we have of the order of 100 gigabytes compressed data. So in order to process all these data, we need a very good processing system which can take these data in real time and create products out of it. And for that, we have an enormous organization we call the Science Ground Segment, which is built, in fact, by the Euclid Consortium. And they can process all these data into data products, which we call. And you would think that it will reduce the amount of data. It is not the case. We will get even more data because the products have larger sizes than the original data. Now, once we have all this data, we can exploit it, of course. So all this data these products will go into a science archive. For the Euclid Consortium, initially, to have a good look at it and to start their cosmological analysis to it. Once on a cadence, on an annual cadence, we release the data to the scientific community. That means that everyone who can access our data archive can do can look at the Euclid images and do science on it. While the next speaker shall tell us much more about what you can do with science, and that is the lead of the Euclid Consortium, that's Yannick Mellier.
Okay. Okay, so the objective of the Euclid mission is to provide answers to the following question. Why is the expansion of the universe is accelerating? Which translates into what is the nature of dark energy? Is it a cosmological constant? It is a dynamical dark energy, that is a substance that may vary, the properties may vary with time, or it is a deviation to general relativity on cosmological scales, what we call the modified gravity model. In addition to that, we would like to know why dark energy dominates the mass energy content of the universe today, and what will be the ultimate destiny of the universe. And we expect from Euclid information to know whether there is a revolution in our understanding of the physical laws of nature from this data. So what Euclid will do is to start from the fact that dark matter and dark energy dominate the content of the universe, but also control its expansion and the formation of cosmic structure in a different ways. You know, gravity is an attractive force, while dark energy seems to be a repulsive one. And the fraction of it will change, you know, the future of the universe. So Euclid will probe the distribution of dark matter and the distribution of dark energy and galaxies, sorry, to an unprecedented precision from space and by using the evolution with time. It will also reconstruct the cosmic history of the universe over the last 10 billion years. So in order to do that, it will use what we call the cosmological probes, one probe will directly observe the distribution of dark matter using the gravitational lensing effect that modify the shapes of galaxies, which are deflected by all the dark matter distribution along a given line of sight. And with that will provide the distribution of the unseen dark matter in all Euclid field. And on the other hand, it will also observe how the galaxies are spatially distributed along a given line of sight by looking at a special characteristic of the distribution, which is called the baryon acoustic oscillation scale. And on the other hand, by looking at the difference between the true distance of a galaxy and its redshift, that shows the peculiar velocity field of the galaxies that unfolds into the massive gravitational structure of the universe. So in order to do that, we are building up what we call a cosmology machinery, which starts from the big survey that Giuseppe and René described already. And and the Euclid satellite will scan the sky with different, many pointings. And for each pointings, we will collect near-infrared photometry in 3 bands. Also, the low-resolution spectroscopy in the same field, and also high image quality with this instrument that will measure the shapes of galaxies. So the spectrograph will measure accurately the redshift, and the photometric data will be combined with an additional extra information coming from the ground-based telescope in order to provide accurate photometric redshift. All this together will provide about 1 million images coming from space and the ground, 12 billion sources spread over 10 billion years, and the best 1.5 billions of these galaxies will be used in order to measure very accurately the shapes of galaxies which are alterated by gravitational lensing and provided the information on the dark matter distribution. Simultaneously to that, we will get 30 million of spectroscopic redshift and 2 billion of photometric redshift in order to explore the distribution of galaxies and the effect of baryon acoustic oscillation, redshift space distortion as function of time. So the consortium, the Euclid consortium, made of 1,600 scientists from 17 countries, will produce the calibrated images and catalog, will measure the signatures of dark energy on wake lensing, baryon acoustic oscillation, redshift space distortion signal, and derive from them constraints on the nature of dark energy. This data will be released publicly during 3 periods, one in 2025, partially, another one in 2027, also partially, representing 50% of the sky, and then in 2030 for the total sky. So from this, and what we have learned during the 10 years of development, is that Euclid, as built today, has excellent performances on the satellite, telescope, and instrument, which means that with respect to the cosmological science, we expect improvement factors on the typical cosmological parameters, a factor of 30 on dark energy model, 30 on modified gravity models, 30 as well on the mass of neutrino spaces, and 50 on the physics of the early universe and inflation model. So in principle, as it stands, Euclid should provide a decisive response on the nature of dark energy. Now it's not enough. We also have now a fantastic amount of data, 12 billion sources, with a unique sky survey with the image quality of the Hubble Space Telescope and near-infrared photometry and spectroscopy for all this data, which is a gold mine for whole field of astronomy for several decades. And we expect from this, information on galaxies, high redshift universe, also solar system object. So, and of course, the main goal of this is really capturing the cosmological parameter that Guadalupe now is going to describe more.
Thank you so much for the introduction to my topic, Yannick. Indeed, I'm gonna give some hints how we are actually aiming to constrain the underlying cosmological model that might potentially best fit the data. So we have started this press briefing by the biggest embarrassment that we have currently in cosmology. We know that 95% of our universe is something that is totally unknown to us, but how do we actually know that it is 95%? This is due to the fact that cosmology, being a branch of physics, is an experimental science. We always aim to test a hypothesis by means of comparing data against a theoretical model and predictions. In this case, in cosmology, we have a really robust model that we denominate the standard cosmological model, but also it's really known as the Lambda-CDM model, that is able to explain most of the observations that we have these days about the universe. This model assumes that the theory of general relativity holds and is also telling us that the main components of our universe are basically unknown. 70% is dark energy and 25% is dark matter. We infer some characteristics for this dark matter, but what is relatively puzzling is that this 70% is responsible of driving this accelerated expansion of our universe that was unexpected. And we like to model as introducing an extra constant in the equations of general relativity that describes the dynamics of our universe. However, this model lacks some really important information that is basically telling us the nature of dark matter and dark energy. And this is why Euclid is essential and is going to be playing the role of this dark detective that will tell us a little bit more about the nature of these dark ingredients. So if we need to give Euclid a homework to-do list, what we would actually like to test? What we would like to test if general relativity holds a larger distance and potentially is the best theory to describe how gravity behaves, or if there is to include some alternative modified gravity models. We would like also to go further in understanding what is the nature of these dark energies, trying to see if we can actually model this accelerated expansion, not using a constant in the equations of the dynamics, but also trying to see if dark energy, as we model it as an unknown fluid, what it would be their properties. We would like to go further and describe more in detail the features and qualities that dark matter might have in order to explain how the large scale structure in our universe is seen. But as every cosmological mission, we are ultimately also interested in understanding how the origin of the universe took place and where was those initial conditions that gave an origin to our universe. This is a model that it is an extension of the standard cosmological model, and we call it W0WA CDM model. And this is the primary target for Euclid to exploit. But how we are going to do this? This is a statistical exercise. So now let me highlight you the overview of how we are going to do this. So basically, Euclid is going to be taking pictures. We need to take several pictures because we need to infer a large data set, as it has been already introduced by my colleagues. From these pictures, we would like to obtain the position, shapes, and distances of a really large number of galaxies. Because with these, we are going to measure some main observables, weak lensing and galaxy clustering, including some of these characteristics of galaxy clustering. We are going to use these observables to compare the W0WA CDM model. And for that, we are going to use Bayesian statistics. We are going to use a statistical approach to make this comparison so that ultimately we could actually constrain some of the components of our universe and the dynamics of how it behaves. So now let me explain you this last point of the pipeline with a really simplistic exercise. Look at this graph. The goal is to fit the data. The more dots we have in this graph, the better we can actually see that the best model that it fits the data is actually a straight line. This straight line only has 2 parameters. So we can say that this model contains only 2 parameters to feed what we are observing. However, in cosmology, it's definitely more challenging. We need to constrain a model that has many parameters. So not only the parameters that tell us something about the cosmology, but also the parameters that contain information of our experiment. That's it, how Euclid behaves. And this is where the challenge starts. We need to fit more than 50 parameters. The ultimate goal is to obtain the best fit of the parameters of these models. Potentially, we could do this exercise with many different models. So actually, the science of Euclid can be increased by a really large number and a substantial, important legacy science. But what it is important to remark is that the challenge in Euclid is to do a big exercise of data science, and also that will require advanced computational techniques to do this exercise. So now that I have actually introduced you what is the statistical challenge of Euclid, we are going to see from our main industry partner how actually Euclid was designed in order to fulfill this important role. So we have Paolo Musi with us.
Okay. Hope you can hear me. So after this deep dive into the amazing Euclid science, I will focus briefly on the satellite, which will hopefully make this observation possible. And first of all, I would like to give a quick status of where we are here in Cape Canaveral. So the satellite fueling has been completed in the past days. And during the weekend, the plan is to complete the encapsulation of the satellite within the fairing in order to be prepared for the launch on the 1st of July. I share now some chart. So I'm representing a large consortium of industry, more than 80 industries in Europe that build the spacecraft, distributed in 20 countries, and with the total industrial value of the contract in the order of 450 million euros. The satellite, okay, now you can see it. It took about 10 years, actually exactly 10 years if we launch on the 1st of July for the industrial consortium to build the spacecraft. And satellite, you see this asymmetric configuration because the cylindrical shape is the baffle protecting the telescope. This is a telescope which combines an high optical quality and a large field of view, as explained earlier. And this combination of two characteristics is not obvious, is not easy to reach. On one side, there is the solar sun shield, which protected the telescope from the sun, because the focal plane of the telescope is designed to stay cold, since there are also infrared sensors installed on it, need to be thermally decoupled from the rest of the spacecraft. Then on the bottom part, you have the service module, which indeed is a very stable, extremely stable platform, because this is needed to preserve the image quality. And we do this with the cold gas micropropulsion, which compensate the remaining forces on the spacecraft, which would move move the image during the image capture. And also with a specially designed fine guidance sensor, which is installed directly on the focal plane of the telescope. A few figures, some of them were already mentioned earlier. Maybe it's good to recap briefly. So it's a medium-sized satellite, but it's still relatively big. It's a bit less than 5 meters tall and 3.5 meters wide. Despite the size, the mass is relatively low, is less than 2 tons. We have a power installed slightly less than 2 kilowatt. The telescope diameter is 1.2 meters, and the field of view is 0.5 degrees. The focal plane for the near infrared observation is to be kept around minus 180 degrees C during the scientific part of the mission. And for this, the point instability of the spacecraft during about 10 minutes of image capture is in the order of 20 micro degree. It's about like 2 centimeters seen from 30 kilometers of distance. And the capability of the spacecraft to downlink data is 850 gigabits per day. Then the actual amount which will be downlinked would depend also on the ground station landing. All this will last for 6 years at least, hopefully in an extension of 1 year. Finally, we went through an extensive qualification and acceptance campaign for this one-of-a-kind satellite. First significant test, I just focus on the last years, was the test of the telescope standalone at cryo temperature, which was done in summer 2021. And then at satellite level, we completed the thermal vibration acoustic campaign and the EMC, the electromagnetic compatibility test. Not to forget that in the last months, we have also successfully, let's say, migrated from a Soyuz launcher, which was the design case for this satellite, to a Falcon 9 launcher. So this complete my overview of the satellite. It was a bit quick, but feel free to ask a question later if necessary.
Thank you very much. That was Paolo Musi from Thales Alenia Space, and we are now opening.
I give the word back, I think, to Nina.
Indeed. Are you hearing me now?
For next part of the conference.
Thank you. We are now opening the floor to questions and answers, and I welcome the journalist to indicate if they have any questions. You can do so by flagging this in the chat here on the side. I see that Teresa Putarova from space.com was the first one. So Teresa, the floor is all yours. We've unmuted your microphone. Welcome. Can you hear us, Teresa? Otherwise, I will read your question. So Teresa is asking, what is the current understanding of the nature of dark energy, and is there still a possibility that it doesn't exist after all? And if it doesn't exist, how will Euclid reveal that? Maybe Yannick would like to answer that, or Guadeloupe.
Maybe I can start answering, and Guadalupe will complement for sure. Yeah, so yes, we will reveal the nature of dark energy because of the property of the organization of dark matter and dark energy as function of time. So these are, what we will see are really signatures of something we don't know and which is not dark matter, because we can separate the two from the analysis of the two components, galaxies and dark matter, from weak gravitational lensing. So is it possible that we reveal that there is no dark energy at all? I would say that if we reveal something, it will be that instead of a new quantum field, for instance, or a cosmological constant, we are facing on a modified gravity on cosmological scale. But otherwise, revealing that there is no dark energy at all or modified gravity is almost not possible, simply because we know from the CMB experiments that the universe is flat, which means that it is a Euclidean universe. And since we know, the fraction of dark matter inside it and ordinary matter, the rest is something else, and it has to be there. So in addition to the observational evidence that we see, because we see the acceleration of the expansion, we also have obvious theoretical evidence that it has to be there. And I think that Guadalupe may certainly complement what I said.
Exactly. I think that from the point of view of your answer, the question of whether it doesn't exist, yeah, I think that you answered pretty well definitely well to the question. Of course, with Euclid, we would like to reconfirm what it has already been seen with other observations, and it is the fact that our universe is expanding in an accelerated way. Then we need to actually explain this extra acceleration, and yeah, what kind of nature this dark energy has, well, it will be referred to the statistical analysis. We will compare different cosmological models that have potentially the capacity to explain this accelerated expansion. And based on the statistical analysis and the statistical conclusions, we will derive what is the model that best fit the data, and potentially could be, yeah, a modified gravity model or something more exotic.
Thank you very much, Guadalupe. The next question is from Tim Stickings from The National. Tim, can you hear us? Tim Stickings from The National. I think you had a question, Tim, about the how Euclid complements the work of the James Webb Telescope. And I think René was quite keen to answer that one. René.
Yeah, I think it's more that James Webb would complement Euclid in that respect. Now, well, the James Webb Telescope is a large telescope. It's a 6-meter telescope operating in infrared, also like Euclid. What Euclid can do is surveying the sky and finding exotic objects, in fact. The main science of Euclid is going to a redshift of 2 to 10 billion years back and scan the whole sky for targets with these properties. However, it will also see targets which are much further away. And this can be used to as a survey for James Webb, who can point them, James Webb can point them to these targets in the longer infrared wavelength James Webb has, in order to have a good specification at the even higher redshifts we are looking for. So in that respect, it would be beautiful if the two telescopes are online and that James Webb could follow up the new findings of Euclid. In the other direction, that Euclid could complement James Webb in the sense that James Webb finds something and Euclid could follow up. I still have to think of cases. I think it's more that Euclid starts with the survey and James Webb is going to specify it in more detail what we find.
Thank you very much, René. Appreciate it. The next question is actually on the launcher, and it's a question for Giuseppe Racca or Paolo Musi. And in this context, I would also like to introduce another guest we're having here, another spokesperson, Loïc Bourrier, who is the head of the collective launch service procurement at ESA. I could imagine, Loïc, that you might want to add something as well. Leo, you are asking if after 10 years of development, suddenly switching to a Falcon 9 launcher just 12 months ago, the question is to Giuseppe and Paolo, you surely never imagined that you would be launching out of Cape Canaveral and not out of Kourou. Are you glad that you're not having to wait indefinitely for a slot with Ariane 6? And how difficult were the weeks immediately after the loss of the Soyuz option?
Okay, I start myself, and then I let Paolo maybe expand a bit. Of course, we are glad that we don't need to wait for 12 months. Actually, I must say that last year, just after very shortly after the war in Ukraine, I was in Kourou to arrange for a planned meeting about the launch with Soyuz, and then. There we were actually still hoping that the war would have finished and then we could have restarted cooperation, etc. Unfortunately, it did not happen, and we were really, let's say, kind of left without any possibility, because at the same time also Ariane 6 was announcing delays, because we had Soyuz as a main launcher, but we always had the possibility to switch to Ariane 6 if Ariane 6 would have been ready. But at the same time, also Ariane 6 was not becoming ready for us. So then we were really left completely in nowhere's land and without any launcher. And you say 12 months, it's actually, we were starting just the very first compatibility study with the Falcon 9, really 12 months ago. But for a while, we were not even sure whether this was possible or not, because as you also hinted there, let's say the fact that you design for one launcher, especially a very sophisticated spacecraft like ours, let's say in other cases it's easier, but in our case, let's say the fact that we could actually switch launch so late, and in the end, we decided to switch launch only 6 months before, because we negotiated the contract with SpaceX only at the end of December. But so I leave it to Paolo perhaps to explain a little bit more the fact that in how we managed to do that. But definitely it was an incredibly tense period, the one because we were after in front of us the prospect of having to store the spacecraft for 2 years or more. So then this was certainly not something that it was welcome, and this was really a big relief to be able to launch from Cape Canaveral instead of Kourou. But I leave the words to Paolo to say more about what this implied on the spacecraft side.
Quickly, I think I would mention three aspects. One, number of analyses to show on paper that there are no incompatibility. This analysis addresses the thermal, the mechanical, the cleanliness, the electromagnetic compatibility, the launch window, and so on. This was more or less concluded by end of last year, when ESA could sign the contract. The second aspect is the testing. We slightly tuned the test campaign on the spacecraft level to show what the analysis had predicted, that is, that we are compatible. But it was only a small tuning. We had not to really change a lot. And the third aspect is the hardware. This is the good news. We can launch in July because we have not to change anything on the hardware. So only analysis and tuning of tests were sufficient.
Thank you very much, Paolo Musi. The next question is from the Wall Street Journal, Eileen Woodward. Eileen, should I read your question? You should be able to speak, but I can read it as well. There are two of them. The first one is, I think, to Guadeloupe, with so much data being collected, will artificial intelligence be used in any of the analysis? And the second question is there a deployment process post-launch in the 30 days heading to L2?
So I can take the first part. If artificial intelligence is going to be used at any point during the analysis pipeline, the answer is simply yes, but this is not something new. In astronomy, we have been using advanced data science techniques for a really long time. In fact, I could actually say that astronomy and other fields of physics are the pioneers of using this kind of techniques to actually be able to process and squeeze the data as much as possible. Simply because one of the biggest challenges is that we need to extract information about so many different galaxies. This is something that it cannot be done by hand. It has to be automized. And this is definitely an aspect in which artificial intelligence will play a role. But I'm aiming to say that it will play a significant role in almost every single part of the full analysis pipeline, definitely also at the end of the pipeline, comparing models with the data directly. Because otherwise it would take such a long time to compare all the models that we would like to test, that we will spend decades. So yes, it's a really important role right now for our pipeline.
I can take the second one about the deployment process. We have these 30 days to reach L2 roughly, and in these 30 days we are basically testing all the various subsystems of the spacecraft to make sure that everything works. We are only deploying one thing, that is the high gain antenna, and that is for Euclid we really needed to minimize any motion of anything. Let's say we minimize at the very maximum all the possible mechanism and deployment as well. The high gain antenna, since we have so many data to send to ground from L2, we need to have a deployed antenna, and that's the only deployment we are going to do. For the rest, we are going to do all sorts of tests on the spacecraft for the first 30 days. And then I can also add maybe, and I probably try to cover also one other question that was later, that in the next following the 30 days, we start making some performance verification of the overall mission. Let's say we want to see that the telescope and the instruments can take the images and the spectra really with the accuracy and the sharpness of the telescope that it needs to be done, as we have explained before. And it will take 2 months to do that. And so therefore, within these 3 months, we will be able to test all what is necessary to make sure that then the mission can really perform the operation properly.
Thank you very much, Giuseppe. I think this has answered some of the other questions that I see here in the chat. I also see that there are quite a few on switching launchers, which I think have been answered for the most part of it, but we will have a close look. So if you still have a question that you find is not answered yet, please drop it here in the chat and we will get back to it. Plenty of questions, of course, also on dark energy and dark matter. Joe Pinkstone, what are the benefits of learning about dark energy and dark matter? Does it affect us on Earth in any tangible way? And is it not a gamble to spend 1.4 billion on something we're not sure even exists with no guarantee we will find it? Who wants to take that question? Several questions, actually.
I can start giving an answer to this. Let's say, since of course it seems to be a lot of money to spend. Let's say 1.4 billion. But first of all, one should always remember that all this amount of investments that a public organization like us does, goes into actually benefit for all the science community and technology and industry. So it goes indeed all in salaries to people. So then it's not an investment that one would do in finance or anything for someone's benefit. This really is a very distributed way of investing money into the society. That's, to me, it's a very important point. The second point is the fact that making progress in cosmology, making progress in physics, in fundamental issues, if you in 2005, the magazine Science had published what is the most important questions we have in science to answer. And they published 125 questions. Let's say the most important questions in science for anything. let's say, not only in physics, not in astronomy, but for any type. For example, there were questions about why the human DNA contains only 35,000 genes, for example. But the question number one was, what is the universe made of? So then this was question number one in science, in general. So then I think it is a very important question to ask. Third, actually, is also that the data that Euclid will gather on ground, even if it will, in case, for example, it will not make a particular discovery on dark energy, is still a huge amount of data, really a huge amount of data in all our extragalactic sky, which will provide, I'm really 100% confident that it will provide an enormous amount of, let's say, byproduct discoveries in astronomy and in physics.
Thank you very much, Giuseppe. We have time for one final question. We're nearly at the end of the hour. Jeff Faust from Space News, he has a question on cost. Not sure if we have the exact number at hand, but he's answering. His question is, what is the additional cost to the mission caused by switching launch vehicles, including the Falcon 9 launch itself, and the extra analysis and testing? Not sure we have that here, but otherwise we can look it up, I guess, Giuseppe.
I cannot reply on the cost of the additional cost, because let's say what we paid for SpaceX is actually commercial confidence. So then I cannot say the numbers. And on the other hand, I also cannot really say much more about the cost of Soyuz, because the cost of Soyuz is fair. Let's say a standard cost of Soyuz and the standard cost of Falcon 9 is fairly well known. Let's say one can check them on the web. Of course, with Soyuz we went already a very long way through, so we had already spent a lot of money. Actually, the Soyuz vehicle are in Kourou, cannot be used, but they are there. So we had already spent a lot of money, and therefore we have quite some extra cost. But I cannot, unfortunately, really quantify, really tell you it is 50 million more or whatever, because I cannot disclose figures about how much we spend for Falcon 9. That is a commercial confidential figure.
Maybe what I can add on a qualitative manner is that the solution that the decision bodies of ESA have eventually taken in a very practical manner to launch with Falcon 9 was by far the optimal solution in terms of programmatic, science, and cost.
Thank you, Loic. We have 2 minutes left. I would like to give them to the New York Times, Katrina Miller, who is asking if we can give a short answer, please. Are there any plans to combine Euclid's map of the universe with other maps that image closer to the Milky Way, like the dark energy camera survey?
I can answer to that question.
Yes, please.
Of course, we combine with other surveys. You know, the Euclid data will be combined with cosmic microwave background observations by Planck, for instance. They will be also combined with current big surveys, like the dark energy survey or the KIT survey or any others. So we will combine all these data with Euclid. What we will emphasize there is the uniqueness of data of Euclid, which is, you know, very wide field imager with high image quality as the Hubble Space Telescope to measure the shapes of galaxies, which is unique. But the cosmological parameters derived from all this data will be also cross-correlated with the rest of the data obtained with different other surveys, for sure.
Thank you very much, Yannick Millier. And this brings us to the end of this media briefing. We will have a quick look at all the questions that were raised, and we'll make sure that those that were not fully answered or were not answered at all will get an answer. And of course, if you have any additional questions, you can contact us at media@esa.int, and we will be happy to follow up. And for those of you that speak German, you might follow in a German version of this media briefing starting right now. And otherwise, I'm looking forward to a successful launch next week. Thank you so much. Thank you very much to the speakers and to the journalists attending. Thank you. See you soon.